Now that we've explored the different theories of acids and bases, we're now going to be going into a little bit more of this conjugate acid-base idea that Brauer-Lonsted introduced. Now, of course, we're going to keep coming back to these concepts because this way the syllabus is written, there's quite a lot of repeated circular concepts mixing together. So we're going to touch on it here, do a little bit of practice. Then later on, when we look at buffers, we're going to come back and revisit this because this is basically what buffers are all about. When we talk about acids that are polyprotic, we're going to come back again. So we're going to find that these concepts are going to overlap, and that's really the way that we learn things. It's very hard to break something up into a sequential step-by-step manner. So if some of these terms are a little bit confusing to begin with, by the time we keep coming back to them and keep doing them, hopefully they'll gel and make them all understandable. It's sort of like doing a puzzle. When we do a puzzle, we do a little bit of corner here, a little bit of a corner there, but then as we do more and more of the puzzle, we start to see the bigger picture. And so by the end of it, what we're hoping for you is that by the end, before you sit your HSC, your chemistry puzzle is complete and you'll be able to see how one bit links in with another, and you'll be able to explain concepts from multiple perspectives. That's what we're aiming for. So let's get into this one here and look at the syllabus. So this here is touching on two sort of areas here. We've already covered properties of acids and bases and terms of Arrhenius theory and Brauer-Lonsted, but we've got the next section which is looking at Brauer-Lonsted in a little bit more detail. So now that we have a basic understanding from our last video, we're now going to explore this a lot more, and it says here, write ionic equations to represent dissociations of acids and bases in water. We've already done that in the last video, but we're going to keep practicing. This idea of conjugate acid-base pairs in solution, and then amphiprotic nature of some salts. And we are going to look at amphiprotic nature in salts in the next video, but we're going to maybe touch on it here too because it's very similar, it overlaps, right? And so here are two examples of salts. So let's get into this amphiprotic nature. So conjugate acid-base pairs, if we were to provide a definition, would be something like this, that in Brauer-Lonsted, the Bronsted-Lowry, in the Brauer-Lonsted definition, we said that we have acids and bases that can accept H+, or they can donate H+. And so by that definition, really, these pairs only differ by a H+, right? So they only differ by one H+ ion, and so they are a partner or a pair. And we mentioned in the previous video this idea of a conjugate. Remember, conjugation is the joining up of two parts, and a conjugate is a pair of something. And so therefore, if we were to looking at ammonia here, that H+ from ammonia gets donated to the base water, because water can accept a proton. So in our Brauer-Lonsted definition, water is a base in this instance. It's acting as a base. And then when that happens, the ammonia, then, which is the acid, forms its conjugate base. We always have acid-base pairs, right? So if we're focusing on this in terms of the acid, then that is going to be the conjugate base, ammonia. Okay. If we were to go the other way around, let's say we're to do another reaction and we're to focus on the ammonia first, like if I was to give you a bottle of ammonia and you were to get that ammonia and place that ammonia in water, then since we're starting with ammonia, we would say, well, that's the base, and that produces its conjugate acid. So depending upon what we're starting with, right, our terminology may change a little bit, but the partners are the same. So here we're starting off with ammonium, therefore we're saying that's the acid, and here is the conjugate base. Now, of course, we have the reciprocal happening on the other side of the coin, right? Here we have water acting as a base. When it accepts that H+, it forms its conjugate acid, the hydronium ion. So these conjugate base pairs exist when they're just the difference of one H+ ion. So let's have a look at these ones here. This is a sort of a question. Identify the conjugate acid base of the following. So it says HCl. Well, HCl is the acid. So if I was to write an equation, then of course this H+ would be donated to the water. and so therefore that would be Cl minus plus H3O plus. And of course, now if this is the acid, and I'm going to shade this in since we have the same colors, so let's go to red. So there's the acid, and then its conjugate base is going to be the chloride ion. So there's one conjugate pair, right? An acid is the HCl, and its conjugate base is the Cl minus. So here we have a hydroxide ion. Now that can't donate a H plus. It can only accept the H plus, so therefore this is going to be the base. And when it accepts a H plus, it's going to form water. So that's going to be the conjugate acid. Remember, conjugate acid-base pairs only differ by a H plus ion. So here we have, it's an incorrect formula there. Alright, this is methylamine, which should be NH2. Alright, so that's the proper formula. If I was to draw it over here, we have N with a hydrogen, now with another hydrogen, and that has a methyl group or a methyl group, and that's called methylamine. Right, and the thing we're going to learn about this in organic chemistry is this nitrogen. Yes, it's got 3 bonds here already, so its octet is satisfied. However, it can accept another electron into its valence shell, right, due to the vacant d orbitals, and it forms a base. So it can accept another H plus, and so it ends up forming this, and then it has a positive, what we call formal charge on the nitrogen. And so this NH2 group, this amine group, can accept an extra proton and act as a base. And this is a very important concept for a lot of chemistry, but specifically if we think about biochemistry in terms of amino acids and making the charge of amino acids, and you know, it's pretty cool. So if I was to quickly just show you, don't have to memorize this yet, but I just want to give you an application of this amine group because it's the first time you've actually seen an amine group. So if I was to do an amino acid, right, the biologists sitting there will know that amino acids are the building blocks of proteins, and you have 20 essential amino acids in our body. But an amino acid has a section down the bottom here which is constant, right? And so here it is here. Whoops, I'm just going to do a hydrogen there. So this is our constant region of our amino acid, and then our little group up the top here, which is called the R group, that changes depending upon the amino acid. But the cool thing here is that we have an acid group which can donate a H plus, but this group here is the amine group which can accept a nitrogen and form a positive there. And this is really, really important when it comes to like separating proteins and amino acids and so forth in biochemistry and forensic science. So the amine group is very important. It acts as a base, right? Once again, you don't have to memorize that little section I told you just then, but I wanted to give you some application of this, and we'll be looking at that later. So if we know that this is a base group there, okay, if this is a base, methylamine, then it's going to accept a proton, and so its conjugate acid is going to be NH3, and we're going to have a plus there, okay. The hydrogen carbonate ion, well, the hydrogen carbonate ion is from carbonic acid, and so it could lose a H to form CO3 2-, but it pretty much does not happen. Okay, the carbonate ion is just way too unstable, and so to lose that, the chances are very low. We're going to look at that later when it comes to looking at different values for that. So basically this is going to be acting as a base here, and so what's going to happen is it's going to accept a proton, and that's going to form H2CO3, and so that is this is acting as the base, and this is acting as the conjugate acid. Okay, all right. So this idea that we have pairs, acid and base pairs, and we can go backwards and forwards by the accepting of a hydrogen, gives us this scenario here, right? And this graphic tries to give you a visual representation of how strong these things are, these conjugate acid-base pairs, right? So if we start off with HCl, it's very, very strong, okay? It's basically going to release its H plus and its Cl minus. That's so strong. It's going to basically completely dissociate. So if I gave you some hydrochloric acid, break completely apart. Which means it's not really going to go backwards. If I had some chloride ions just sitting in the water there, they're going to be surrounded by the water, but they're not going to really react with a H plus to form you hydrochloric acid. Not going to happen. So in this instance here, we have complete dissociation. All right. When we go down the list, it gets weaker and weaker and weaker. So for example, if we have some hydronium ion here, that's going to dissociate to give you water, but we know that this can go backwards, so we could, we want to do, write a reverse arrow there because that can go backwards, right, to a greater extent compared to hydrochloric acid. Then we get down to medium here, where we have phosphoric acid. Okay, that can go backwards as well. Then we have acetic acid. We know acetic acid is very, very weak. We've said before that about 98 to 99% of it exists in this form in terms of the equilibrium, right? So we know that if we have some acetate ions there, they can react with the H plus to give you acetic acid, neutral molecules. Okay, and so what we're doing here is we're getting an understanding that we have differences in terms of their strengths of dissociation. And that's going to become really, really important when we go to explain the acidic properties of salts. Okay, I'm going to give you one example now that we're going to look at later. But let's say I was to give you some ammonium chloride salt. Okay, and we know that according to Arrhenius, it doesn't release OH minus ions, and there doesn't seem to be any H plus ions going on there. But this will dissociate to give you ammonium and chloride ions. Okay, but we know from our acid-base conjugation pairs that if we have ammonium, it has the ability to do that. And so ammonium can react with water, and it will donate that H plus to water to give you ammonia, but will also give you a hydronium ion. And there's the acidic properties of ammonium. So we can use this understanding of conjugate acid-base pairs. Here is the acid, there is the base. The acid here produces its conjugate base. The base produces its conjugate acid. So we can use this understanding of conjugate acid-base pairs and our understanding of whether it's weak or strong to determine if a pH of a salt is going to be acidic, basic or neutral. We're going to look at that in more detail in later videos, so don't freak out. We're going to do a little practical and measure the pH and predict and write equations, etc. But I wanted to give you some context. I wanted to give you some understanding of why we're telling you this, of why we're going through acid and base pairs. There's a reason for it, and the reason is because once you understand conjugate acid-base pairs, not only can you explain why some substances produce acidic solutions, but you're also going to be able to explain how buffers work, and that's in the next video, and touching on the next video I should say, where we're looking at amphiprotic substances, because what we're talking about here, some of these have the ability to donate or accept multiple hydrogens. So I'll see you in that video. Alright, before we go to the next video, I want you to check out more courses that we have here on our YouTube channel, which are just small snippets from the actual bigger courses that we have on theflipteacher.com. Of course, with all of our courses, we try to incorporate practical sessions. We have study cards, we have posters that you can print off and stick around your room and do a lot more. We have up to 68 or more videos per course. That's like 9 to 10 hours of material that really delve deep into the syllabus and looking at essential content, skills, mathematical manipulations, and a lot more. So if you like that, go over to theflipteacher.com and check it all out, and I'll see you in the videos.